Back to the small session on vibration. So last time we stopped here. We got the equation for x in terms of t. Now there are two constants. So we started off with a second degree differential equation. So we enter with two constants. So we can evaluate these constants from these initial conditions. X at time t0 at time 0 is equal to 1 and velocity at time 0 equal to 0. I'm not showing you. Once you plug in this initial conditions, we will arrive at some equation of this kind. Okay, so finally we got what we are looking for. We got an expression for x in terms of time. So if we plot it, it will be something of this kind. See, this is x, this is time. There are few observations that we have to make from this graph. So at time t equal to 0, we have an initial displacement. So it is matching with whatever initial conditions we gave. And another thing is the response. This is called basically response. So the response is periodic. So this repeats after a finite time. So that time is called time period. Time period is given by 2 pi omega n. Now we can go back omega n. In the earlier lecture, I defined omega n as root of k by m. It is the natural frequency. So, appreciating from a physical point of view, natural frequency, so you have a system. Once you leave the system after a slight excitation, that is the frequency at which it will vibrate. So that is a physical relevance of natural frequency. Natural frequency has a unit of radians per second. Usually it is also expressed in hertz as well. So in order to convert it from radians per second to hertz, we have to divide it by 2 pi because we know one cycle is 2 pi radian, basic mathematics. So I explained you the concept of natural frequency and explained you the concept of time period as well. Another key fact in undamped single degree of freedom vibration is, see, the amplitude is not changing. So that is what I have to discuss for the single degree of freedom free undamped oscillations. Thank you.